now I would like to invite our next speaker, Simon Nørrelykke. I apologize if I completely... Perfect. Simon is the head of Image and Data Analysis Unit of the Scientific Center for Optical and Electron Microscopy, most popularly called ScopeM at ETH Zurich. As I know him, he's a bioimage analysis guru. He's working at the interface of physics, biology, and computer science with the current focus on applying deep learning to biomedical image and data analysis problems. He is a physicist by training, and he started out in econophysics, which means physics of complex systems, and he holds a PhD in physics from University of Copenhagen. Welcome, Simon.
Thank you. Thank you all for being here. Let me know if I'm too far or too close to the speaker, to the microphone. Like that. Thank you. Okay, so first thing is I'm curious which version we got because I gave them two versions, the last one over lunch, but we'll see. So I'm Simon, as it says, and that'll take me forward. Or the other one. It does. Okay, so I'm going to talk a little bit about images like what you're seeing on the screen right now, but also this is a little bit of a cheat because I'm not really going to go into projects specifically like everybody else has been doing so far, because I am truly working in a facility. And it's not that I embrace it, I just accept the facts. Right? So this is who we are when I say the facility. It's myself, I'm a physicist, or at least I once was. It's Shumon Stoma, who is a computer scientist, or once was, and Andrea Sepira, who is a bioinformatician, and still is. So I'm from Denmark, they're from Poland. We all now live and have permanent positions here in Switzerland. That's us. We are part of ScopeM, which is a sort of a significantly larger undertaking of approximately 40 permanent staff, which is 30 full-time equivalents. It's a microscopy facility. They do lab automation, sample preparation, and we have about 700 active users. Lots of machines also. And we service all of ETH Zurich, plus industry, and whoever wants to pay for the services. And that, again, is part of ETH Zurich, which is what it is. So what do we do? And when I say we, now I'm back to the three of us who do image and data analysis. Well, we do user support for image analysis that we either charge or give away for free. That's a part of it. Then we give internal support to our microscopy friends. We teach, actually more than 20%. We also build and maintain IT infrastructure. And then, of course, there's overhead, because there always is. And then also we have 20% for R&D. And we all know that 20% for R&D, that means you can barely read the papers that come out. So there you go. And if you go on a one-week conference, that was that month's budget, right? Okay. We have various projects, and I'm going to list them in two different ways. First, I want to say, though, that they're almost exclusively in biology, right? Also, they're mainly light microscopy. That's what I mean by LM. But we do see an increasing number of electron microscopy projects. That's EM. So the biggest ones we have in light microscopy are high-content screening campaigns. They run over multiple years. Initially, it's just like trial and error until they get the protocol to work, and then they finally image all the data, and then you get busy crunching your data. There's a considerable infrastructure overhead just for computing and storage and all of those things, and that's why the users typically come to us, because this is significantly above what your average biologist can handle. Some can, right? Then we have sort of more, you're playing with the microphone. Good. All right. Light and electron microscopy projects, sort of tabletop experiments, you could say. So it's a single user, it's a single project, and they just come to us, and they don't last years. They should last days, weeks, possibly months. And classical projects are like count objects, right? Measure co-localization, intensities, quantify features. And for that, we mainly use open source software and some custom written code. And then increasingly, we're taking a deep learning approach, both in high content screening, that's HCS, and in LM and EM. And I will talk a bit more about that next. Another way of classifying projects is by the duration and whether we charge or not. So often the entry point is image clinics. as we call them. They're just office hours, right? But it means that people know when they can come and disturb us to ask for advice for free. Actually, they can just sign up on a web form, so it's easy. We give them for free. They're one-on-one. We give about 50 per year. They might lead to what we call free trials, which is we might invest another half to a full day on support on this project afterwards, either as a trial, or often it can lead to a complete solution of the project. And we do that because we do want to help people, and we don't want to start by saying, welcome, this handshake was 80 francs, right? Because then we keep people away, and that's not our goal. We're not doctors. Well, we are actually, but a different kind. Not that kind of doctor. And then, of course, we have paid projects, which is if the free trial points to that we can do something useful and they can convince their PI that it's worth the money, then we might start working on sort of longer projects. And they're charged by this rate that I mentioned before. And of those, we may have 10, 20 per year. The larger collaborations, which typically are high content screens, but they can be something else that just drag out for a long time, has a lot of data. They're often organized with a lump sum payment, and they can last for, as I said, years, and we don't have many of those. Teaching. I said we teach, and we absolutely do. So we give a recurrent 3-day introduction to Fiji, which is ImageJ, which is like the de facto standard among biologists, among life scientists, essentially. That's the number one image analysis tool that they know, or think they know. And then occasionally we give sort of 1-day trainings in PhD schools, and then we have our own yearly 1-week-long summer school, ZIDAS. We ran this since 2017. The last 3 years with EPFL, and this year also with Basel and Bern. So it has spread out, it's taken off and has a life on its own now. And it'll actually take place in person here at EPFL this year. And then we teach in various other schools. Among them, I would maybe highlight the EMBL, Deep Learning for Image Analysis, which is a different beast altogether than the other things we teach because, well, let's say they're more advanced people that participate in it. Now, you might ask, why do we teach if we have all these other things to do? Well, one simple answer is we have to. It's part of our job description, it's what we're hired to do. But another reason is that, we enjoy doing it, but also it scales a little bit better. It's not like making a MOOC, right? But it scales a little bit better than just doing the project for the user. If a user comes to us with a problem and we solve it, that doesn't really fix it longer term. But if you can teach that user how to solve them and understand them, then the user can fix it him or herself the next time, and may even also teach colleagues in the lab how to do it. Okay, I thought I should have an image at some point, since I talk about image analysis. So here is a super interesting image, right? Very challenging. No, obviously not. You can segment this image blindfolded, essentially. So these are DAPI stained nuclei. So the white blobs are fluorescent signal from DNA that has been stained. So these cells are also fixed and dead. So the challenge isn't so much to segment this one, because as I said, anything will do here, essentially. The challenge here is that this would be part of a high content screen, so you have 100,000 of those images, and obviously not all of them are going to be in focus, and not all of them are going to be with cells. It's going to be junk and gunk. So there are all these little things that you have to deal with. So, okay, you segment it, it looks like this. Not very interesting. Classic methods are fine. They used to be like bread and butter image analysis. Now they're almost not even that any longer, because the tools that are freely available and easy to use have basically taken that off the table. And so, in a sense, we're not sad about that, because, they are not very interesting, right? So it's great if a user can do it themselves. However, that was one channel, right? Here comes one of the other 3 channels. This looks worse, right? This is the RFP, the red fluorescent protein channel. And what you have here is the exact same view. It's the same cells as in the other one. And here you have stained one particular protein. It doesn't really matter which one. And the user would like to quantify it, right? Now, that's often actually what they lead with when they come with images. I would like to quantify my images. Good. Now we have to have a little discussion about what they mean by that, because I can easily tell them what the mean intensity of the image is, but it doesn't really help them. So quantification could mean count the number of spots of foci, or it could mean measure the entire intensity, or something like that. And so here it's important that we understand enough about the scientific question, the biology, to know what is good enough, what will actually help them answer their question in a, let's say, very robust manner if it's a high content screen. So a little bit about projects and constraints, and introducing this, I introduced the concept of what is good enough, and I'll get to that again. The question, therefore, is often not whether we can do a project, but rather whether we can do it in days or hours. Right? Anybody can do it. I mean, anybody can build a super sports car if you give them $1 million, right? But try and build something funny for 20,000. That's hard. That's the smart car. And it's obviously no Porsche. Unlike researchers, we don't have just a few projects. That's the other thing, right? That we work on for years. We've all been postdocs and so on, so we know what that is like. We tend to have significantly more tens of projects, and they vary in both size and duration. And another constraint, apart from time, is that the users, or rather the PIs, typically don't want to pay us for spending multiple weeks or months working on something. Especially given that the PhD student or postdoc is often, in a sense, for free, right? Because they're on a grant already. It's not real money any longer. They have to pay for it. So although we can maybe do it in a month, and they can do it in half a year, and not at the same quality, they will still go for the latter option. Many PIs, of course, do realize that this is money well spent, right? And they do come to us. So I don't want to make it too bleak. Okay, so, but anyway, the offshoot is that we rarely do have time to develop our own tools. And it also means that we need to operate with good enough. Right? And here the good news is that if the signal is indeed very strong, like the DAPI stained cells, then, you know, a stupid method, a weak method can be good enough. Right? Strong signal, method can be weak. Now, not having time to develop tools, we tend to just use and adapt existing ones. And here we sort of have a luxury problem, because unlike 10, 20 years ago, where you would be lucky to find just one piece of software that could do sort of roughly what you wanted to do, now the problem is actually to figure out which one to pick, because there's so many that will solve your problem. And of course, what that means is that we have to stay informed about what comes out. So lessons learned from that little part is that good enough is actually good enough, and perfect is the enemy of done. But I mean, you all know this. Also, it's rarely worth adapting a highly specialized, learning or adapting a highly specialized tool for the perfect fit for the last couple of percent. Typically, it's better to just take a tool you already know really well and then use that one, right? So what we recommend is that you master a few tools that cover sort of different problems. And of course, go for polyglot tools if possible, ImageJ, Python, something like that. Here are the 5 that we use the most to sort of take different corners of the landscape of image analysis. Bioimage analysis. ImageJ Fiji, it does roughly everything, and is known by roughly all biologists, very roughly. Thousands of plugins, and now also pre-trained neural networks. Cell Profiler and Soil Profiler Analyst. It's sort of one of the first, it's the mother of no-code workflows in bioimage analysis, I would say. First coded in MATLAB, then in Python later on. And that's for segmentation and classification of cells. Elastic, pixel-based, QPath, pathology, but also now you can pull in deep learning tools. Animalis, it's commercial, but the newest version actually opens up for interfacing with open source. I have about 10 minutes, correct? I'm going to pretend I do. Okay, so when these big 5 are not enough, then we need to build sort of more specialized standalone tools, or get to know them. And here, this particular link will take you to a list of 1,000+ annotated tools for bioimage analysis. And increasingly just Python for data wrangling anyway. Implement open source tools such as Startist, CellPose, CSP Deep. Who's heard of these words? Who's heard these words before? 2 of you, 3 of you. Okay. Scikit image, obviously, and zero-cost deep learning for microscopy. Worst acronym ever, right? This is Startist. It's from roughly 2018. It was developed by Uwe Schmidt and Martin Weigert. Martin Weigert is now a group leader here at EPFL. What it does is, and what it does exceedingly well, is segment star-shaped objects in 2D and 3D. And it also allows overlap, which is very rare in an image segmentation method. It exists as a pre-trained Fiji plugin, and that means that it really gets out to the users. And it also exists as I'm abbreviating it as zero cost, right? But a zero cost notebook, but that's zero cost deep learning for microscopy. All right, that's Startist. CellPose is a little bit like Startist, except it's a little bit newer and it's trained on massively more data. So it's significantly more robust, and it uses a completely different, rather different approach. So it doesn't need the objects to be star convex. So it takes more of a diffusive approach to figure out where the cell begins and ends. Comes as a web interface. You can just go to that link, and then you can drag and drop your image and say what kind it's like, and then see what it does for you. Or you can just download it from GitHub, or you can interface with it through GitHub, through QPath, or. CSP Deep is a deep learning toolbox for microscopists. It's one of the sort of earlier, but I mean, early days in deep learning is what, 4 or 5 years ago, at least when it comes to microscopy for image analysis. Florian Hug and et al. More or less spearheaded this one, the application of deep learning for microscopy image analysis. And initially, this toolbox only did restoration, but now it also does segmentation. So now I want to say a little bit about zero-cost deep learning for microscopy. For those who don't know about it and might be interested, it's a toolbox for what it says here, easy implementation and running of essentially cutting-edge but open-source deep learning code. And it is implemented in Google Colab, and that means that you don't have to worry about getting the environment up and running. And if you're a biologist, that's a very good thing. And they also make their notebooks available in sort of a curated fashion, so if you can do intelligent copy-paste, you can do this, right? And most people can do that. So the good thing here, or the difference here between just using a plugin in Fiji that's pre-trained and using the notebook series, that you're not confined to using pre-trained networks, you can train them yourself here. Right? So that's the whole selling point here. So here are examples. I don't know whether we can do links work. If they do. Okay. Do I allow this? It'll just show you a brief little video. I think you can follow without me talking. But in case it wasn't clear, it's just showing a handful of the tools that exist as notebooks in zero cost. So these are the tools we have at hand now for free, right? There's no way we could build those ourselves in our 20% research time. So we're very happy that the deep learning has happened and taken off. Thank you, gamers of the world, who made GPUs cheap. And thank you to these researchers, of course. This is super cool, right? This is synthetic fluorescence. It guesses what color and where, not what color, but where a nucleus would be based on the surroundings. Okay, let me see if we can get out of this before we get commercials. Okay, so then I don't have to show these things. Oh, this is again actually fluorescent, synthetic fluorescence. On the left you see the input image, on the right you see what it guesses as output. It's a little bit scary. This is image restoration. I'm going to skip over that. These are the existing, or a big fraction of the existing pre-trained networks you can use in zero cost. You see that it is a significant number by now. And these are the people, there are like 30 people involved in this, right? So 30 people working 100% not on this, but on research, more or less. Obviously, 3 guys with a 20% budget, there's like a factor 50 difference here. We love these guys, we're happy they exist. Okay, we don't only do service, we also do research. But actually we don't, right? We only do research when we can hire a postdoc to do it. That's not unlike most PIs, I suppose. The only difference being that it's harder for us to get the money for it because research requires funding and funding requires research, which requires you get it, right? And we're sort of out of that loop because we don't publish that much. However, there are a few grants you can get. Novartis for Innovation and SNF Spark is a chance for you. Does that mean 30 seconds or 2 minutes? Okay. Challenges, and then the nice one. So challenges, we have to deal with with avoiding being forgotten in publications, and you can be forgotten for any number of reasons. Some of them listed there. And then we also have to adapt to the changing model and targets because we are part of ETH, and ETH has a Schulleitung, which has a whatever, and they set the price point for us, and it's not something we get asked about. So our price point has gone from 0 francs an hour to 75 francs an hour to 80 to 40 and back to 80. We've been steady on 80 for some years now. Let's see what happened. And then we have to figure out a way of dealing with users when they say, how much is it gonna cost? Because, I mean, it's research. What do you think? Have it done in 3 days, right? 3 months later. It's just really hard to guess at this. And then, of course, no, I'm going to skip that. Benefits. Benefits for us, for working in such a setting, is that we get an exposure to a wide variety of scientific projects. That's interesting. We get a chance to teach, which is great if you like it. And we don't suffer from the publisher perish. It's more like publisher languish. It's a softer version of it. So it's less stressful than being in let's call it full-on academic research. And we get to play with many new developments, right? Because we have to. For the user, it's good because we can help them, and we are a human interface. It can be hard for a biologist to go on Google and search for find my cells, right? They don't know the word segmentation to start out with. Right? It's just, there's a little bit of jargon there. So it's good for them to be able to talk to somebody who knows enough biology to know what they mean, and they can translate it into the relevant terms. And for the host, I would say, meaning for the university, it increases overall the quality of the research done at the university. That must be an advantage overall. And it also allows smaller groups, newer groups that are not 40 big and therefore can afford one image analyst, but are maybe just 5 or 10 people. They can come to us and get expert support without having to have it themselves in-house. And with that, last slide, thank you. Here are some links. Swiss Bios, us bioimage analysts in Switzerland, we are no longer alone. We created a little association for us. Join if you're interested. The forum, that is the place to ask for bioimage analysis, ask questions, or just get information. And the plug for SIDAS, the Switzerland's Image and Data Analysis School, which takes place here in June, and we open for application today. So, thank you.
Thanks a lot, Simon, for this very insightful talk, and especially pointing out these really valuable resources which we can use for bioimage analysis. So now, I already see a raised hand, so we have a first question here.
So my question is, you say that you are hiring, but what fields exactly? Is from microbiology or deep learning with focus on some science?
When we hire, you say? Yes. Well, I'm basically open to, if we were to hire people, it would be anybody who can do bioimage analysis, right? And it can be a biologist who is really good at coding and being quantitative, but typically there are more people that can code that have learned a little bit of biology, right? But it can be a mathematician, it can be a computer scientist, so physicists are sort of a little bit everywhere because, and engineers. But I know of a few biologists that are extremely good coders and developers, right? And they have the great advantage that they know the biology significantly better than we do. I mean, we pick up a few words here and there. So if you can do the job, then you can do the job.
Yeah, Thank you for the talk. How do you make people want to work with you? Is it the word of mouth enough for you, or do you have specific strategies that, like during the courses or during workshops, trainings, or some other strategies? Yeah.
Well, I can tell you what we're not doing, but what we should do. That's more interesting, maybe. We're not knocking on doors, going to professors, giving them a little pitch deck and giving them the spiel about what we can do and how we can empower their research. We should do that, but we haven't really done that because if we do that, we're going to get projects and we don't really have the manpower to do those projects, so that's a problem. So it's a little bit like word of mouth, and then we have the image clinics. We give these lectures, and also many of our users actually come through the facility, and that's simply, they might ask the microscopists how to do something, and they say, go talk to the experts. Right? So internal word of mouth, let's put it that way.
Hi, I'm Vincent Greg. I like to know, it's maybe a bit technical, zero cost DL for MIC. You use it at the level of data, like for data augmentation. Let's say that you would like to see if there is an infection in a blood with a parasite, you would use it to transform your data set into the different pictures. Is that the way we use it?
The way we use it depends a lot on the particular question in mind. You ask sort of more of a scientific question, and we would have to try and break that down into sort of the relevant image analysis questions. It can be used for the synthetic fluorescence, which you have to be careful about, right? Because it shouldn't be dreaming up things. It'll only show things that are there. It'll only sort of show things that are there that a trained person can see, but now it's easier to see because it's shown explicitly. For segmentation, definitely we use that, yes. But also just for sort of classic enhancement, using sort of just denoising, for example. For that we will use it, yes. But really it's a matter of understanding what the scientific question is and then sort of tie these together.
Okay, great, thank you.
Do we have another question?
Did I understand that right? You say the cost per hour is not defined by you or by ScopeM?
That is correct.
It's coming from ETH up. So it's
yeah.
more like a steering tax.
Yeah, and they're trying to equalize it. That's why sort of it jumps a little bit up and down. I mean, initially it was...
Do you know how much percent it is for you as of the coverage of the...
Oh, I think ScopeM is supposed to recover about a third of the budget or something like that, roughly.
Okay, so we have time for one last question.
Maybe a question related to the previous one. So how you funded? So the society hour. Yeah.
So we used to be part of a department, and I actually think it's great to be part of a department because you get a personal contact to users. But now we are a so-called central technology platform. Well, EDA is part of the central technology platform that's called ScopeM. So they're on the shoe lighting budget, right? They have their own number in the spreadsheets. Let's put it that way. And that's stable funding, and that's why they wanted it, because if you're on a departmental budget, they might throw you out to hire a professor, right? So stability is good.
So thanks a lot.
Thank you.
Simon.